So hello friends, I am your class instructor Vivek Kumar Tiwari for the subject that is material science and metallurgy, and what we have discussed in the last class you probably be knowing. So you are all observing. I hope that you are all seeing the videos which I am regularly uploading on YouTube. Plus I am also sending the same videos again and again on our official website also, official WhatsApp group also. So I hope I am daily putting one video on the WhatsApp, that is official group. And in the last class, you know that we have started with the unit number 3 in your syllabus, and that is ferrous and non-ferrous metals. And then we have discussed about the classification of ferrous metals as steels and cast iron. And then in the steels, there are different type of steels, and we have focused our attention towards the learning of the stainless steel and its types. Basically, we have learnt about the 4 types of stainless steel, that is known as austenitic stainless steel, ferritic stainless steel, then one more is austenitic stainless steel, then ferritic stainless steel, martensitic stainless steel, and one more stainless steel called as the precipitation stainless steel. Then we have seen another type of steel called as the tool steels, and under that we have seen again 4 types of tool steel, that is hot working tool steel, cold working tool steel, then special purpose, and one more is there which is called as the high speed steel. We have discussed about all these different type of stainless steels and tool steels. Today we are going to learn about one more type of steel called as a high strength low alloy steel. So high strength low alloy steel is the topic of discussion in today's class, alright, and the further things I will be opening up all those discussions slowly in this 1 hour of lecture. So high strength low alloy steel means this thing, that it is low alloyed steel, which means the percentage of alloying elements is low, but it shows very good strength. And one more important thing what you should remember about HSLA steel is that it is weldable. So usually the problem associated with ferrous metal, not many metals, but some of the metals show this drawback, that it is not weldable. In particular, low alloy or low carbon steel, the problem associated with is that if you take such 2 metal plates and try to weld, they will not get welded. So this is the problem associated with low carbon content steels. But here in this case, that is HSLA, the advantageous thing is that this kind of steels, that is high strength low alloy steels, are easily weldable, and they contain low alloying elements, and if the alloying elements are low, then the price of that component also will be low, and at the same time it shows very good strength. So this is the understanding, or the you should know what is the meaning of HSLA alloy or stainless steel. So it is called as high strength low alloy steel. These are basically low carbon steel. Okay, the percentage of carbon is lower here. Then that means if the percentage of carbon is lower, they are very good. They show good ductility, malleability, formability, and weldability. And they also have low alloying elements. As I said earlier, the alloying elements are very much low. Basically, they are weldable, and the applications, if you see the applications of HSLA steels, it is like this. The huge tanks which are used to carry the milk and water from one point to another point is made up of HSLA, because you have to weld the various sections of this steels. So it is expected that the steel should be weldable, and for that we make use of this type of steels called as HSLA steel. This kind of, and you can see the welding being done at different portions. Right. Similarly, this bridge is which is there. This is called as I think it is a Howrah bridge of our Kolkata. It is also made up of the HSLA steel, which is weldable. So this type of steels, if it is weldable, containing low carbon and low alloying elements with showing good amount of strength, then those type of steels are called as HSLA, that is high strength low alloy steels. I hope you have got or understood the meaning of this, right? HSLA, high strength low alloy steel. So the strength is high, alloying elements are low, carbon content is also low. Because the carbon content is low, it should show actually lower strength, but because of the low alloying elements and because of the alloying elements what you have added in low quantity, the strength becomes higher and they are weldable. So this is the understanding. Then next what we have to discuss is about what is the effect of this alloying elements on the steel. So you know that we add alloying elements into the steel. Steel is basically alloy of iron and carbon. You add some kind of alloying elements into it. For what reason? To improve its property. How does this alloying elements change the property of the metal from the metallurgical point of view, if you want to see, will be discussed in the subsequent discussion. So what is the effect of the alloying elements? See, I have written that alloying elements affect the iron carbon diagram and the properties of steel. Basically what happens is that if you see from the iron carbon diagram perspective, if the alloying elements are added, they change the lines of the iron carbon diagram. The iron carbon diagram will be somewhat distorted and somewhat different shape if you have some kind of alloying elements into that steel. That is the first point. And alloying elements affect the relative stabilities of alpha and gamma ion and also A4, A3, A1 temperature lines. So I have told, when I was telling you about the stainless steel, I had told that some type of stainless steel contains more amount of chromium in it, and chromium are basically ferrite stabilizers. Similarly, I had said that one more kind of stainless steel will show more amount of nickel and manganese into it, and nickel and manganese are austenite stabilizers. So what basically this kind of alloying elements does is that they distort the iron carbon diagram and they try to stabilize some of the regions or some of the phases seen in the iron carbon diagram. So because of that, those phases are visible or easily available even at room temperatures. This was what happens when you add the alloying elements into the steel, right? Alloying elements can be of two types. One is called as the ferrite stabilizer and another is called as the austenite stabilizer. So the alloying elements, when you add, they can be either of ferrite stabilizer or either it can be austenite stabilizers. Example for the metals which are ferrite stabilizers are chromium, tungsten, W means tungsten, molybdenum, vanadium, and silicon. These elements are ferrite stabilizers. They stabilize the ferrite phase in the iron carbon diagram or in the steel, and some elements are austenite stabilizers. Example, manganese, nickel, cobalt, and copper. So these are the elements. I think we had asked a question in the IA also that tungsten is what type of stabilizer, whether it is austenite stabilizer or ferrite stabilizer. The answer was here. Then we'll see what is this ferrite stabilizer. So ferrite stabilizer, what does it do? Ferrite stabilizer will stabilize the ferrite phase present in the iron carbon diagram. So what it does is that it will shift that A1 line up, and because of which that A1 ferrite phase becomes more dominant in the steel. So this is what I have shown here. If you see, this is the iron carbon diagram, and where is the ferrite region seen? This is the region where the ferrite region is seen. So what happens is that when you add the ferrite stabilizers into the steel, what happens is that this line, which is called as A3 line, this line which is called as the ACM line, and this line is called as A4 line, all of them shift towards inside, and because of which this ferrite phase becomes more and more dominant in the steel. This is also depicted over here. So if you see this graph, you can see that this is the carbon percentage temperature. As you go on increasing the carbon percentage from 0 to 15%, you will see that a rhombus kind of shape, that is from here to that that rhombus shape goes on shrinking more and more, and because of which you can, in other words, say that the ferrite phase becomes more and more stable in the steel. This is what happens if you add the ferrite stabilizers into the steel. I hope you have understood it. You see that this is the iron carbon diagram, and this is the iron carbon diagram, and this is the region where the ferrite phase is present. So if you add the chromium into the steel, what you will see is that this line and this line plus this line, all this line goes on moving towards the inside portion of the iron carbon diagram, because of which this becomes more dominant or this becomes visible. Even this line goes on going down, and because of which this graph or this line or this region becomes more dominant in the steel. In other words, the steel what you will be having, and if it contains chromium in it, then it will show ferrite phase at even room temperature. So that is what is called as the ferrite stabilizer. Similarly, if you see what happens with the other type of stabilizer called as the austenite stabilizer is like this. So when you add the austenite stabilizer elements into the steel, what you will see is that because of that austenite stabilizer, you will see that this line, A3 line and ACM line, will move down, plus that line and that line also will move up. In other words, what you will be seeing is that the austenite phase, this region becomes more and more dominant. You can see that this line is going down and down and down and down like this, and because of this, this region becomes more and more prominent. In other words, you will see that even at room temperature, you will be able to see the austenite phase in the steel if you have added the austenite stabilizers. So by the addition of austenite stabilizers, what you will be happening, what you will be seeing is that this region will become more and more dominant even in the room temperature, and even at the room temperature, you will be seeing the austenite phase in the steel. This is the effect of the alloying elements, that is in particular ferrite stabilizer and austenite stabilizer. Okay, I hope you have understood this. So this is the austenite phase. You just look into the I am hovering the mouse in the slide, just observe that. So with the addition of the Austenite stabilizers, we will see that this line, A3 line will move down, ACM line will move down, and because of which this austenite becomes more and more stable even at the room temperature. The effect is shown in the form of a graph like this. Okay, so this is what is the effect of the alloying elements on the properties of the steel. Now we have discussed about the ferrous metal, and in that we have discussed about the steels, and in particularly we have discussed about the stainless steel, we have discussed about the tool steels, we have discussed about the Hsla, that is high strength low alloy steel. These are the three type of ferrous metals which you had to learn. Then again one more type of ferrous metal, that is the cast iron, is what we are going to discuss in subsequent discussion. Cast iron is also a kind of ferrous metal, means it contains iron in it. And then what is the percentage of carbon? Yes, in the last class I have said cast iron will contain the percentage of carbon from yes, you are right, it is from 2% to 6.67%, while steel will show the percentage of carbon from 0 to 2%. This is the difference. So cast iron, like steels, are basically alloys of iron and carbon only. The cast iron contains the carbon percentage from 2 to 6.67%. High carbon content, because of the percentage of carbon being higher in case of the steel cast iron, it is relatively brittle in nature compared to that of your steel. So cast iron and steel is there. If you check the brittleness of those both material, you will see that steel's brittleness is lesser than that of cast iron. What is the reason behind it? The more percentage of carbon into it, that is from 2 to 6.67%. Hence high carbon content makes cast iron very brittle. Commercially manufactured types are in the range of 2.5 to 4%. You should remember that nobody will go for the highest percentage of carbon content in the steel. It will be just around 2.5 to 4%, right? Then cast irons can be rolled, drawn at room temperature, that is its malleability and ductility is very good. They can be melted easily and casted into complicated shapes, hence the name cast iron. This I have also explained in the previous iron carbon diagram, that the cast iron region is also called as castings. Why? Because cast iron shows a very good fluidity. It can be melted easily and it can be poured easily, and it fills up the mold cavity very easily. That's why it is called as casting. And that reaction what precedes this kind of operation is the eutectic reaction. I said eutectic reaction is the region at that point the cast iron, though an alloy, will behave just like a pure metal and its fluidity will be very good. Okay, so that is the thing. They can be melted easily and casted into complicated shapes. Cast irons are cheap, they are cheaper, and there are four types of cast iron which we are going to learn, that is white cast iron, then malleable cast iron, then grey cast iron, and spherical graphite iron. Coming to the white cast iron, a white cast iron, if you try to break a fracture cast iron which is white in nature or white cast iron, you will see that the fractured surface will show white surfaces or white microstructure. So that's how we identify the white cast iron. Okay, we identify the white cast iron. It is also called as white iron. It is the only member of cast iron in which the carbon is present in the form of carbide, while in all the other subsequent cast iron what we are going to discuss, the carbon will be present in the form of graphite, black color thing, while here it is present in the form of carbide. That's why it shows whitish in nature when it is fractured. Produced by chilling selected areas of a casting, preventing graphite formation. So graphite is not being formed here, so that's why it is shows white microstructure or white cast iron. They are extremely brittle, difficult to machine, used where resistance to wear is more important, and example are the liners of the cement line mixers, ball mills, etc. So these are some of the components which are made up of white cast iron. So white cast iron are used wherein there is an loading kind of wear type of loadings are being applied on the metallic components. So such places, or the inside liners of the cement mixers, all those things are being made up of the white cast iron. The next type of cast iron is what we are going to discuss is the malleable cast iron. So here this cast iron is obtained from the white cast iron. Here you should remember that this type of cast iron, malleable cast iron, is being obtained from white cast iron. Here the carbon is in the form of carbide. The properties are just opposite to that of the white cast iron. They are not brittle in nature, they are malleable, and that's why the name malleable cast iron. They can be machined easily, and they are used in making of flanges and valve parts. So in the earlier case I have shown you the white cast iron's microstructure also. So you can see this is the microstructure of white cast iron. So here you can see that majority portions are whitish in color. That's the understanding behind why it's called as white cast iron. So now when we see the malleable cast iron, they are malleable in nature. That means they can be drawn into thin wires and shapes, thin sheets. And then these are some of the components, the flanges of the wall parts. This is again the flanges, this is the wall component, again a T-shaped wall component. All these things are made up of malleable cast iron. This is the microstructure of the malleable cast iron, how it looks like. Then grey cast iron, the next type of this cast iron is grey cast iron. So here this is important that it is widely used. The most widely used type of cast iron is grey cast iron. Okay, it is one of the oldest type of iron which human beings are being using. Grey cast iron means cast iron. For many people, cast iron means what? Grey cast iron, and grey cast iron means cast iron. For them there is no much of a difference between them. Grey cast iron is also named because its freshly fractured surface has a grey appearance. So if you take a grey cast iron and try to fracture it and see, you will see the greyish appearance on it. So that means it is grey cast iron. This cast iron contains graphite in the form of flakes. So here you can see the microstructure. Here the carbon is in the form of graphite form and it is in the form of flakes, hairy kind of structures. So because of this, these are called as the graphite flakes or graphite cast iron. I hope we have demonstrated the microstructure of this in the lab also, our metallurgy lab. We have shown you the specimen, kept it under the microscope and shown you the graphite flakes present in the cast iron. That's how you identify the grey cast iron also, right? So the presence of these flakes in the iron makes them show good machinability and good damping property. So you might see or try to wonder that what are these microstructures and how does this affect the final mechanical properties of the metal. So this property of this metal showing this graphite flakes does affect the final property. So because of the presence of this hairy flakes, the damping property of the final steel and even the machinability of the steel becomes more. So this is an advantageous fact. However, if more amount of this is present, then it is also a decreasing aspect for the mechanical property of the metal. So it should be present in a very optimum manner. This you have learnt in our metallurgy lab also, right? That the morphology of the graphite flakes plays a very important role in the determining the final mechanical properties of the metal. So that is that. So graphite flakes are stress concentrators. So these are the points at which the stress what you apply on the metal will be getting concentrated. Grey cast iron is widely used for making of machine bases, then engine frames, drainage pipes, pump housings, etc., which requires good compression bearing capacities. So where this kind of grey cast iron are being used, grey cast iron or this type of cast iron are used where in such situations wherein a large amount of damping loads are being applied. Compression loadings are applied. For example, you have a machine part, the machine part is being vibrating. For example, a motor is there. So because of the vibration, what happens is that the machine's life will get down. So in order to damp that vibration, what we do, we put a grey cast iron base on the floor. On that we erect our machine and keep. So because of which what happens is that the damping is being observed and the vibration of the machine comes down. And for that base, you make use of the grey cast iron. So grey cast iron are basically used for this kind of situations or applications like machine bases, engine frames, then the drainage pipes. You might have come across the drainage pipes on the roads and all. Those are made up of the grey cast iron only. The pump housings, etc. The pump housings what you see are made up of this type of cast iron. And the basic requirement is that it should take up the huge amount of damping properties. Okay, and the microstructure, if you see, which is very important for us, is like this. It will show the microstructure will be like this. Here you will see that there are presence of graphite flakes. These are graphite flakes with a ferrite matrix. So matrix will be there at behind. Ferrite or perlite matrix will be there, and then there will be flakes of graphite. Flakes of graphite. So these are some of the the applications of the grey cast iron where it is being used. Then the next type of this cast iron is the spherical graphite iron or SGI iron. So SGI iron is also known as ductile iron or nodular cast iron. This we have discussed in the lab. That's why I'm just moving ahead quickly. Okay. So this SGI iron is also known as ductile iron or nodular cast iron, and they show the carbon in the form of graphite, and that graphite is in the form of tiny black color balls. So that's why, or nodules, that's why it is called as spherical graphite iron, wherein the carbon is present in the form of spheres, nodules, right? Hence the interruptions are lesser, increasing the tensile strength and toughness. So what happens is that because this morphology of the carbon is in the form of tiny nodules, this metal can take huge amount of tensile strength, and it is used in such situations. Again, one more important thing related to SGI iron is that SGI iron is considered equivalent to that of the steel. Many of the people in industries take or consider SGI iron as steel only. Okay, so this is an advantageous point for the people who work in industries. For them, they are getting the property of the steel, but the cost is not as that of the steel also, right? So Hgin is such a one metal which has the property of that of steel. Okay, so I've just said that Hgin are popular due to their improved properties. They combine the advantages of cast iron as well as the steel. This point you should remember, that they combine the advantages of both iron and steel. That's why it is very much widely used in industries. And the microstructure will show spherical graphite nodules, this kind of graphite nodules, plus matrix of perlite. So this black color thing is the matrix, and that is made up of perlite. So these are some of the components which are made up of the spherical graphite iron. In particular, they are used in making of crankshafts, automobile door hinges, then pistons, cylinder heads, motor frames, etc. So basically these are all the different type of cast iron. Okay, so what are the different types of cast iron we have discussed? The different type of cast iron what we have discussed is white cast iron, which will look white when fractured. Then we have seen malleable cast iron, which are actually malleable. Then we have discussed about the spherical graphite gray cast iron, wherein the microstructure will show graphite flakes. And we have seen about the spherical graphite iron, wherein the carbon is present in the form of graphites, and it will be round spherical in nature, and it is also widely used, and it has the property equivalent to that of the steel. So these are the four type of cast iron what we have discussed. So understood? If we discuss about the stainless steel, there are four types. Those are austenitic, martensitic, ferritic, and precipitation stainless steel. When we talk about steels, there are four types of tool steels again: hot working tool steel, cold working tool steel, then high speed steel, and special purpose tool steel. Then when we talk about the cast iron, again under cast iron there are four types. One is white cast iron, malleable cast iron, then your spherical graphite iron, and gray cast iron. So every type of ferrous or non-ferrous metal will have again subdivisions into it. You should be knowing about that. Okay. And that is why studying each of this metal becomes very much difficult, and that is why there is a concept called as the structure to property relationship, which we have learnt in the first unit. So rather than learning the different type of metals, we just go for the structure what they possess, and if they show that type of structure, then definitely they should possess those particular type of properties. This is the basic on which the material science subject is standing on. I have told you that previously also. Okay, so with this we have completed about the discussion of ferrous metals. Now we will discuss some of the points, very brief points related to non-ferrous metals. Okay, so we will discuss some of the points related to non-ferrous metals now. See, non-ferrous metals are the one which will not contain iron in it. So those metals which do not contain iron in it are called as non-ferrous metals. So the name only will say non means no, ferrous means iron. So any metal or alloy which does not contain iron in it are called as a non-ferrous metal. Then majority are made up of the alloys of copper, aluminum, magnesium, nickel, lead, and tin. So majority of the non-ferrous metal, if you see, they are aluminum based, they are copper based, nickel based, tungsten based, like that. Okay, we will look after copper and aluminum alloys. So what we will do is that there is the study will go on. We cannot complete all type of non-ferrous metals in this one UG course and in some one or two classes. So we will focus our attention only towards the some of the brief properties and features of two type of non-ferrous metals, that is, or alloys, that is aluminum, and the other one is copper. So we'll start our discussion with the aluminum alloy. Aluminum alloy is the best characteristic feature of aluminum alloy. Can anybody tell? What is the best feature of aluminum alloy? You might have had an experience of holding an aluminum plate, or many a times you have an experience of seeing the aluminum metal, observing it, touching it, holding it, lifting it. You might have seen that it is very much light in nature. Aluminum metal is very much light in nature, and only because of this light property, it is used in n number of engineering applications. What are the engineering applications which comes to your mind when lightweight is asked about? It is aerospace, because there is flight, aeroplane. Then automobile, movement is associated with the automobile, so it has to move, it has to be light. Even the medical areas, the stretcher, there are n number of medical components which has to be light in nature, and for that aluminum has to be used. So basically aluminum is very much famous because of this property that it possesses, that is, it is very much light in nature. So the best known characteristic of aluminum is that it's lightweight, better strength to weight ratio, means the strength is very high and the weight is very much low. So if you take the ratio of strength to weight, strength will be higher, weight will be lower. And good malleability, they are easily malleable, Malleable means they can be converted into thin sheets. High corrosion resistant, they do not corrode as compared to that of your steels or cast iron. They don't show corrosion, they don't rust, and high electrical and thermal conductivity. Electrical and thermal conductivity, if you see, of aluminum metal is also very good. If you want to know, the first metal which is given the first 100% of electrical conductivity is silver, and then comes aluminum. Okay, if you see the density of aluminum, it is around 2.7 gram per centimeter cube. It is considered as, or it is compared to steel. You will see that the density of aluminum is 1/3 of that of steel. 1/3 of the density of steel is aluminum. That is why aluminum and steel cannot be mixed together. Aluminum will always float on the steel. Why? Because aluminum metal is lighter compared to that of the steel. If you see the density, you will understand that. That is 2.7 gram per centimeter cube. And it shows FCC structure. So I have told you that any metal which shows FCC structure means that that metal will be highly ductile in nature, very much ductile in nature. You can take the example of gold, silver, lead, tin, aluminum. All these metals show FCC structure, that is face-centered cubic structure, and face-centered cubic structures are basically very much ductile in nature, right? This is one more example for your structure to the property relationship. Then pure aluminum tensile strength is around 13,000 psi. Okay, melting point is around 660 degrees Celsius. The melting point of pure aluminum is 660 degrees Celsius. It cannot be welded. Just one thing you should remember, that aluminum is very difficult to be welding. Welding cannot be done on the aluminum metal. To increase its strength, alloying elements are added. Aluminum, to increase its strength more than this what its pure metal is having, if you want to increase its strength, you have to add some alloying elements. That is the concept why you add the alloying elements. Aluminum alloys are aluminum silicon, aluminum copper, and aluminum magnesium, then aluminum tin. So aluminum can go and combine with this kind of elements like silicon, copper, magnesium, tin. With this different type of elements, it can combine and form a alloy. The very much famous alloy of aluminum is aluminum silicon alloys. The very much famous alloy of aluminum is aluminum and silicon alloy. So I have put a aluminum silicon phase diagram also over here. This is a phase diagram for aluminum silicon alloy. Okay, so you can see this diagram and tell me what are the reaction happening here. Where is the reaction happening and what type of reaction is happening? Please observe the phase diagram and tell me what is the reaction happening over here. Yes, you can see that the liquid line, or here there is a phase called as liquid. It is getting transformed into a solid phase. So here basically liquid is getting transformed into a solid. So what type of reaction is happening? It is eutectic reaction. So liquid getting transformed into solid at this point is called as the eutectic reaction. You know that when we have discussed about the phase diagram. So you can see that the melting point of the aluminum is this one. The melting point of silicon is somewhere over here. But an alloy of this one, that is 12% of aluminum plus silicon, will show a melting point very much lower than that of the silicon. So that is why this is used. So aluminum silicon alloy will not have a melting point at that of 1414 degrees Celsius or 700 or 660 degrees Celsius. It will be something around 400 degrees Celsius. So you can see that aluminum metal will melt at this temperature for this percentage alloy component. That is the usage of this aluminum silicon alloy. That's why it is very much widely used in the industries, aluminum silicon alloy. This is the phase diagram for that. Preferred where good castability and corrosion resistance is needed. As I said, it can melt very easily. That's why its castability is very good. The silicon content ranges from 8 to 13%. So you will see that the percentage of silicon is around 8 to 12% shown over here. That much percentage. Then the addition of silicon to aluminum increases its fluidity, making it suitable for casting. So silicon you basically add to the aluminum for what reason? To increase its casting ability, fluidity. It can melt easily and flow inside the mold and fill the mold cavity completely. For that reason you make use of it. Aluminum silicon alloy forms a eutectic at 12.6% silicon is basically in casting. This percentage. At this percentage it undergoes a eutectic reaction. This is what we have learned previously also. So one more important fact about aluminum copper alloy, which is also called as duralumin, which is used in making of the fuselages or the bodies of aircrafts, is that the aluminum copper alloy, which is called as duralumin, shows age hardening. Under heat treatment chapter we have discussed that. What is age hardening? Age hardening is, we have seen that the metals will show hardness over a period of time or after a period of time, and then after that some period of time the hardness will decrease, which is called as age hardening. Now aluminum copper alloy or duralumin shows this property, that is age hardening. And that is the reason why before the usage of this aluminum copper alloy, it is being stored in the refrigerator so that its hardness shouldn't reach to the optimum level and decrease. So till that time it is kept inside the refrigerator, and once the requirement comes up, the shopkeeper will remove the part duralumin alloy from the refrigerator and hand over it to the customer for forming it and using it in the different places. So that's what I have written. This point we had put it in the IA also. So aluminum copper alloy, duralumin is an example used in making of rivets for aircraft construction. Since it is a natural aging alloy, it is refrigerated to prevent aging. Whenever required, it is formed and used. So whenever it is required, it will be removed from refrigerator, formed means change the shape, and it is being used for the application. So again, aluminum magnesium alloy is one which is basically used for seawater applications. For seawater applications, you basically go for aluminum mixed with magnesium alloy, while aluminum and tin alloy is used for making of cast bearings and all. For making of bearings and all, aluminum plus tin alloy is being used. So these are the different type of aluminum metals and its alloys. Now we will go ahead with the last type of non-ferrous metal, that is copper and its alloys. Okay, so one of the most useful metal and one of the previous very old type of metal, non-ferrous metal, which was used by human civilization is this copper. It is reddish yellow in appearance. So if you have a copper metal, you will see that it is reddish and yellow in color. It is very it shows a, or it has a very good appealing appearance to the people, and it is FCC structured. Again, it shows FCC structure. That is why it can be drawn into thin wires like this, or it can be drawn or made as thin sheets like this, right? So density of copper is around 8.9 gram per centimeter cube, and melting point is around 1356 degrees Celsius. It is one of the considered as the second best material in terms of electrical conductivity. So the first metal which is considered as the best suitable for electrical conductivity is silver. The second one is copper. And good corrosion resistance is shown. However, pure metal is very weak and ductile. If you take 100% of copper and try to use it, it is not possible. So you have to alloy it with copper. You have to alloy it with some other elements like nickel and all. Okay, copper is being alloyed with nickel, zinc, tin, like that, so that its strength increases. So because of that, we have seen, we come across two type of alloys for copper. One is the brass and the other one is the bronze. Brass is made up of copper and zinc, and bronze is made up of copper and tin. So this is one thing you should remember. Brass is made up of copper, more amount of copper, small amount of zinc, and bronze will be made up of copper and small amount of tin. So these are the two alloys of copper. So right, so brass is an alloy of copper and zinc, and under that there are two types, alpha brass and alpha plus beta brass. I'll not go much into detail. This you have seen in the lab also. And alpha brass where it is being used, and alpha plus beta brass where it is being used. So alpha brass is also a cold working brass, and it is red in color. So reddish color copper alloys, if you see, you should understand that it is alpha brasses. And alpha plus beta brass is also called as duplex brass. It's hot working. This is basically for cold working, low temperature working. This is used for high temperature working applications. So these are the things about the copper and its alloys. So this is a graph or a image which shows the different type of copper and its alloys. So you can see this is alpha brass. It is yellowish in color. So this is how it is being identified, yellow color. It is alpha brass, and this one is alpha plus beta brass. It is reddish in color. Both are the alloys of copper only. Both are the alloys of copper. So here again I have put a table over here. So this table will show you the different type of non-ferrous metals like aluminum, titanium, copper, iron, and the crystal structure what it shows. Like for example, aluminum shows FCC structure, titanium will show hexagonal close packed structure HCP, copper shows FCC, iron shows three different type of structures. What are those three different type of structures called as? It is called as the allotropic forms of iron. That at different temperatures, the different type of crystal structures are being shown by the iron. That is what is mentioned over there. You can see that at room temperature, iron will show BCC structure from and then it shows, you know, FCC structure, and again the structure comes down to BCC structure. This is what has been depicted over there. Similarly, the density of the different type of metals is mentioned. For aluminum, it is 2.7, titanium it is 4.5, copper is 8.9, and iron's melting point is 7.8. So basically we are trying to compare this non-ferrous metals, that is aluminum, copper, titanium, with iron, that is a ferrous metal, which is a ferrous metal. The melting point of the different type of metals: aluminum it is 660 degrees Celsius, titanium it is very high, 1660 degrees Celsius, copper 1356, and iron it is 1560, 35 degrees Celsius. Specific heat and other thing, all the properties of the metals are and non-ferrous metals are mentioned. For example, the tensile strength of aluminum is around 700 MPa, for titanium it is 1400 MPa, for copper it is 220 MPa, and for iron it is 1600 MPa. This is the reason why iron and its alloys are used in n number of applications, because of its very high strength, 1600 MPa. Just see. And aluminum it is around 700 MPa. This is the reason why aluminum is also used. However, more widely used is steel. So these are some of the properties of our different type of non-ferrous metals. So what I would like to say you all is here is that we would like to stop down our discussion about the different type of non-ferrous metals only to this one. Okay, so because these are all the different type of non-ferrous metals, their properties, features, applications, and again the list will go on. So what we have done, we have just seen across the properties, microstructures, and applications of these type of metals, that is ferrous metals. In that we have seen about the steels, and under steels we have seen about the stainless steel, then the tool steel, Hsla, this we have discussed. And under cast iron we have discussed about the white cast iron, malleable cast iron, grey cast iron, and spherical graphite iron. Then we have seen aluminum, and under aluminum we have seen the different type of alloys like aluminum copper, which is also called as duralumin, aluminum magnesium, aluminum tin, which is used in the ball bearing applications, aluminum copper magnesium is used for the underwater applications. Like that we have seen. Then we have seen the copper non-ferrous metal, and under copper we have seen the basic two important type of alloys of copper, which is called as brass and bronze. So this is just the overview of the different type of ferrous and non-ferrous metals that are used in industries and day-to-day life and engineering applications. So with this, your part of the ferrous and non-ferrous metals are over. Now only one thing is left, is about in the complete, of course the complete subject only, this part is left, that is how to test the material. So you have the material with you, you are able to suggest a material for a particular application. Now there would be a requirement that you have to test the material. How to test the material? How to evaluate the properties of the material, like tensile strength, compressive strength, impact strength, then fatigue strength, creep strength. So there are how to evaluate that and see that this suggested material is suitable for that requirement. So for doing that, we have certain type of tests, and those tests are nothing but the material testing part. So the next discussion what I am going to do in the next class would be about only material testing, how to test a material, and about each type of test what are the important things what you should be knowing. And in particularly we are going to discuss about tensile test, which is widely done in the world to understand or evaluate the properties of metal. We will be discussing about the compressive strength, which is slightly little lesser used. We will be discussing about the hardness test. Hardness test is the most important and widely and most easily done test to evaluate the mechanical properties, and there is a relationship between this hardness test and the tensile strength, test of the material. So just by doing the hardness test, you can evaluate the tensile properties of the material also. So that we are going to learn. Then we are going to learn about another test called as the impact test. Then we are going to learn about the creep test, and then finally we will end up our discussion with the fatigue test. So basically we are going to learn these 6 type of tests which is done on materials to evaluate its properties. First one is tensile test, second one is compressive stress test, the third one is hardness test, then there is creep test, fatigue test, and then one more is there which is called as the impact test. So these are the 6 type of tests which we are going to learn in the next class, and with that the complete portion for your material science and metallurgy will be over. So again I would like to brief about, we have been discussing about the unit number 4 in our discussion in 2 or 3 classes. It is called as ferrous and non-ferrous metals and material testing. The first part is ferrous metals. Under ferrous metals we have discussed about steels and cast iron. Under steels we have discussed about the stainless steel, tool steels, and Hsla, that is high strength low alloy steels. Under cast iron we have learnt about white cast iron, malleable cast iron, then grey cast iron and spherical graphite iron. And non-ferrous metals we have discussed about aluminum and its alloys and copper and its alloys. That completes your ferrous and non-ferrous metals. So just what you have to do when you are coming for your examinations or you are preparing for the examinations, you should be knowing this classification and each of these ferrous and non-ferrous metals, its applications, its properties, microstructure, some of the salient points you should be remembering and coming. Then the thing is to know about the material testing, which we'll be discussing in the next discussion. Okay, so I would like to stop down over here. Thank you so much.